Hello, we are going to start section 1.2. In section 1.1, you learned what a differential equation is and how to identify whether the differential it's a ordinary differential equation or it's a partial differential equation. And also, you learned how to determine whether the differential equation is linear or not, and what is the order of the order of the differential equation, and also the independent and the dependent variables. So in 1.2 now we were going to look at what is a solution, or what do we mean by solution, and how do we present the solution of a differential equation, and also we will learn what is an IVP and how do we solve it. Okay, so there are bunch of these vocabulary or definitions, so I will go through them. I think I will split this section in 3 videos because I want to make shorter videos. So in one video we will just discuss these definitions, and then in the next 2 I will do examples. So we say a function y is equal to phi of x. Now why do we say y is equal to phi of x? Well, why don't we just leave it like y? Well, the differential equation will be probably in y. It could be any variable, but let's say the dependent variable is y. So if we have an equation like this, dy by dx equal to some function, let's say fxy. So solution will be, of course, we want to find the y, but y is going to be a function. Now you can call it phi of x, f of x, g of x, whatever name, it doesn't matter. But like equations, when we are solving equations, what are the solutions? The solutions are numbers which, when plugged into the equation, they satisfy the equation. Those are called solutions of the equation. Now, with differential equations, we don't have numbers. The solutions are not numbers or just numbers. They are functions, because remember, we have to differentiate them. So if we have a number, the different derivative of a number is a 0, so it doesn't work through. But that doesn't mean that a constant or a number cannot be a solution of a differential equation. You will notice that 0 is a solution of a lot of differential equations. I think almost every differential equation, probably. And then, it is called a trivial solution. But we are more interested in non-trivial solutions. Now, so we just understood that a function, when we plug it into the differential equation, it should give us the left hand side and the right hand side of the dE should be equal. Then we say the y is equal to phi x is a function of the differential equation. Now, the solution of a differential equation actually come with the intervals, are accompanied by intervals, and these intervals can actually impart some important information about the solution. So since we are saying we have intervals, so we say now the solution to a differential equation on an interval a, b. So this is the interval a, b. Notice here the a and b are not included. And is any function y is equal to phi of x which satisfies the differential equation on that interval. Now, we can have the solution in different forms. So we can have an explicit solution, implicit solution, a general solution, or an exact solution. So what is an explicit solution? If you recall, maybe at some stage you might have seen this. If you have a function or an equation y is equal to x squared plus sine x minus 5, then this is called an explicit equation, because the y, the dependent variable y, is written on one side and it is alone, raised to 1 power, and the right hand side is just a function of x. So this is called an explicit form of the equation. So if our function is given like this, then we say our solution, is something like that. Then we say it's an explicit solution. Implicit solution will be when it is not explicit. So for example, this is an implicit equation. If it is a solution of a differential equation, so we say it is an implicit solution. Now, you remember you learned in Calc 1 implicit differentiation. So that's how you can differentiate this and find the dy by dx. And I believe in exercise section 1.1, some of the questions ask you to do the implicit differentiation. Okay. The next thing is initial value problem. So initial value problem, abbreviated as IVP, it is nothing but a differential equation. The extra thing here is there is some extra information given, which is the initial conditions. Now, initial conditions depend on the order of the differential equation. If it's a first order differential equation, then only one condition is given. So the number of conditions is equal to the order of the equation. So, and these initial conditions are basically values of the y values or the function value, and the I would say value of the solution, which we have to find in general, but some typical values of the solution are known, or in other words, the function values are known at certain points, a function and the derivative and all. So if we have an equation dy by dx is equal to fxy, then the initial condition given will be y of x sub 0 is equal to y of 0. So now, and if we have a second order differential equation, then we will be given two different initial conditions. So for example, if I have d2y by dx2 plus dy by dx minus 2y equals to 0, then if it's a IVP, I should be given one is the value of the y at x naught, and then we should also have a value of the y prime, the first derivative, at x naught. So x naught is the same. So x naught will be the same for all the initial conditions, and but of course the y values will be different. Okay, so now what do these initial conditions do actually? So what they do is that they let us find the exact solution. If you recall, in Calc 1, you must have learned something like, what if you anti-differentiate? Oh, actually, let me do it like this. Let's say we have the differential equation dy by dx equals 3x squared, and I want to solve this. So then what will I get? Well, y will be equal to antiderivative of 3x squared dx, so it's just 3 times x cubed over 3 plus a c. If you recall, we put a plus c. So this is called the general solution. So x cubed over 3, 3 and 3 get cancelled, so we just get x cubed plus c. So this is the general solution. Now, particular solution or exact solution. So if you see what this is a cubic moved, shifted up or down, because plus C means if C is positive, shift up, C is negative, shift down. So let's draw or sketch some of these. So I have the cube graph, something like that. This is 1, 2, 3. So this will be when C is 0. Now if I have C is equal to 1, then my graph will be something like that. And if the C is 2, something like that. If C is minus 2, something like that. Okay. So now when you notice here, what we have is bunch of, we say, family of curves. So the general form shows the family of solutions. So which solution is our answer or which solution is our solution, that depends on the initial condition. So now if we were given some initial condition here, so for example, if I was given that y of 3 is, or maybe y of 1 is two. So what will I do? I will plug that in my function that I found. So my function is y is equal to x cube plus c. So I plug in 2 for y and 1 for x. So I can find out c. 2 minus 1, 1. So c is 1. So it means we are talking about this solution. So this will be the exact solution. Okay. Now, but on which interval? Well, because our solution or x cube is a polynomial, so the domain is all real numbers. So this is a solution on all the whole real number on the interval negative infinity to infinity, and of course the 1 is contained is this interval, so that will be the interval of validity. Now this is a very important question that you will see over and over again in like almost every chapter. We will have to discuss this existence and uniqueness of the solution. So what this means is that when we have a differential equation, can we figure out if there is a solution? And if there is a solution, our question will be, is it unique? And so first, two parts. First is there a solution for the given differential equation, and is it unique? Okay, existence and uniqueness. So then for different types of scenarios, we will have different theorems that will explain under what conditions you can have a solution of your differential equation. Most often they will be talking about the solution of a IVP. So what theorem 1 is saying here, that consider the initial value problem, dy by dx is equal to f of xy, where y of x at x naught is equal to y naught. So if we have a first order differential equation, IVP actually, initial value problem, then if the function itself and the partial derivative of the function with respect to x if they are both continuous functions in some rectangle. What do we mean by rectangle? Now notice here, f, the function is it looks like it is in implicit form. This side, right hand side, because it says fxy. So there is x as well as y in there. Could be, right? So then, what do we mean by rectangle? Rectangle means that you have AB is the interval AB, or the value of x is between A and B. So this is the interval AB. So x is going to be somewhere in between here. Now we can have same situation for y. The y could be between two numbers. So let's say C and D. So that C is less than y is less than D. Now if we draw these horizontal and vertical lines, you will see that we end up getting a rectangle. I am going to draw them dashed because remember the endpoints are not included. If I draw solid, it means the endpoints are included. So see this rectangle inside here? That's what we are talking about, the rectangle R. And so we represent it by this set. We write it like this. R is equal to the ordered pair, or all the points x, y, such that, so this is a very common way of writing, describing something using a set notation. So here we write what type of thing we are talking about, and then what are the conditions on it, and that gives you the set. Okay, so it says, so if we have this situation that the function is continuous on that interval that we saw up there, and also the x naught value and the y naught, x naught, y naught point, I should say, must be in that rectangle. So somewhere in here should be the x naught, y naught point. If this is the situation, then this theorem 1 says then the initial value problem has a unique solution. Phi of x in some interval. Now the solution is not going to be on the rectangle. The solution is going to be on the interval. On the interval, x naught minus delta is less than x is less than x naught plus delta. So what does that mean? How do you interpret that? So it is basically an interval around x naught, or with center at x naught. So for example, here is your number line and here is your x naught. What we do, we go to the right some a little bit and pick a point here. So in order to write the the value related to this, I have to add something in x naught. So I say x naught plus a delta. What is delta? Delta can be anything, but it is a positive number. And then go to the left and subtract delta from this. So this interval, which contains x naught, so we will have a solution on this one. So this is how we will proceed in our examples. So I will stop here and do another video with or maybe two other videos with the examples.